Now we come to the main topic, simple harmonic motion. We will study the situation under which a body executes simple harmonic motion. The first requirement for a simple harmonic motion to be executed is of course force. No motion can be caused without application of a force. But in case of simple harmonic motion, the force becomes proportional to the displacement that you make from the mean position of a body. What do you understand by the word mean position? Actually, there is a word called stable equilibrium. The systems like block spring, the bob of a pendulum when it is at rest are called stable equilibrium. If you disturb a body from the position of stable equilibrium, then a force is produced which tends to minimize the disturbance and bring it back to the position where it was there. It is as if the body doesn't like it and it wants to be restored to its natural position. That is why the word restoring force. So, in case of simple harmonic motion, when you apply an external force, the body accelerates according to Newton's laws of motion. But the moment you leave the force, a restoring force comes into play. And if this restoring force is proportional to the disturbance that you have caused from its position of stable equilibrium or stable position or rest position, then there is a chance that simple harmonic motion will be executed. Why I tell chance? Because mere proportionality of the force to the disturbance is not enough. The force must be in the opposite direction of the displacement. It is quite obvious. If it is not an opposing direction, it will continue to move further and further and will not come back to the equilibrium position, meaning by it will not be restoring force. So there are two basic requirements for execution of simple harmonic motion. One, the force acting on a displaced body must be proportional to the displacement. This is the first condition. Second condition, in mathematical terms, F must be proportional to modulus of x. Why I tell modulus of x? Because if we take, this is the rest position, if we disturb it by this side, we can call it positive x. If we disturb it by this side, we can call it negative x. The force must be proportional to the extent of displacement. This is the extent of displacement, and in this case, this is the extent of displacement. Since the displacement can be either in the positive or negative direction, we choose to make it neutral. F must be proportional to x. The second thing is that the force which is proportional to the displacement as described above must be a restoring force, meaning by it must be opposite in direction to that of displacement. Remember, displacement is a vector, so the force must be opposite to the displacement. F is equal to minus kx. This is often the formula. The force, the restoring force, F restore, must be is equal to minus kx, where k is a proportionality and x is the displacement caused. These are the two essential conditions for SHM. In fact, a third condition should be there if you are if you want to make it more accurate. The third condition is that the body must be in a state of stable equilibrium. Before the disturbance happened. Body must be in a state of stable equilibrium. Actually, when any physical system is in a stable equilibrium, you make a small displacement from the mean position. It has been seen that a restoring force appears, and the restoring force E is not only proportional to the displacement but also opposite to the direction of displacement. So from a stable equilibrium, if you displace it, it is going to result in a simple harmonic motion. The example of stable equilibrium are a pendulum which is displaced slightly, not large angles but displaced through a slight angle. Block spring system where a block is tied to the spring and spring is at rest. A marble which is oscillating in a ball in a small angle. All these are conditions of stable equilibrium where the disturbance caused creates a restoring force to minimize the disturbance itself,